Hello, everyone. Good morning. My name is Gustavo Bruci. I'm part of the Population and Health Work Group of the Brazilian Association for Population Studies, ABEP. And today we are going to present our third scientific session, which has the objective to debate themes related to population health and mortality. So we had our first scientific session. We had the pleasure to receive Professor José Manuel Aburto, presenting the significant impacts of the COVID pandemic on the United States racial mortality. In the second scientific session, we had the pleasure to receive Professor Elisenda Pérez presenting the gender differences in health life expectancy in Spain. So you can all access both presentation in a web page on YouTube. And today, I would like to present Professor Ugofilippo Basellini. Ugo is a research scientist and chair of the research area Aging and Generational Process at the Laboratory Digital and Computational Demography in Max Planck Institute for Demographic Research in Rostock, Germany. And also he is an associate researcher at the French Institute for Demographic Studies, INED, in Paris. His presentation today is about new perspectives in mortality forecasting. And to debate with him, we invited Professor Everton Manuel Lima from the University of Campinas in Brazil, who also has experience in mortality methods. So we would like to thank Professor Ugo and Professor Everton for participating, and thank you all who are following us on YouTube transmission. So Ugo, welcome and feel free to share your presentation.
Hello, everyone. Thanks a lot. Let me try to share. Let's see. Okay, I guess you can see the slides. So thank you very much, Gustavo, for this very kind invitation, and thanks to the Brazilian Association of Population Studies. I'm really glad and honored to have been invited to give this talk. Of course, I would have liked better to be there in person and talk with you in real face-to-face, but this is the new kind of standard. I hope we will go back to some more normal interaction. But anyway, I'm super excited. And thanks also to Everton for accepting to discuss my talk. I'm very looking forward to a stimulating conversation with him and with all of you in the audience. All right, so as Gustavo mentioned, today I will be talking about mortality forecasting. So let's start by outlining some motivation for why forecasts of mortality are important. Well, in particular, forecasts of mortality are very used and very useful for assessing, for example, the sustainability of pension schemes, insurances, elderly care provision, but also to, for example, predict population aging or to project populations, and several other type of projections depend on mortality forecast. There has been a revived interest in the field of mortality forecasting in more recent years, especially thanks to the seminal contribution of Lee and Carter, who in 1992 introduced the well-known Lee-Carter model to forecast mortality. This model basically takes a matrix of log death rates, log of MXT here, and describes it with the three set of parameters, alpha x, beta x, and kappa t, which represent the general shape of mortality, that is alpha x, and then the beta x kappa t capture, well, kappa t captures the general level of mortality at time t, and bx, the general pace of change in mortality given a change in kappa. So if you want the rate of mortality improvement at age x. And one of the reasons why this model has become so used and basically the benchmark approach to forecast mortality is that it's pretty straightforward to derive forecast of mortality for the entire age-time surface, the only thing we need to do is basically extrapolate the time index kappa t. And after 30 years of its introduction, the Lee-Carter method is still the benchmark approach to model and forecast mortality. So today I would like to give you some different perspectives on these topics, on themes that I've been working on in the last few years. In particular, I structured this talk made up of two different parts. In the first part, we will look at forecasting the age-at-death distribution. And in the second part, we will look at forecasting cohort mortality using the Lee-Carter method. So I will start from this. That is a project on which I worked during my PhD a few years ago. So it's a joint project with Carlo Giovanni Camarda from INED, who was at the time my PhD supervisor. And let's start by giving some motivation for this project. Well, we have seen that the Lee-Carter model, but also a lot of different approaches that have been proposed in recent years to model and forecast mortality, these are generally based on mortality rates. And you can think of mortality rates basically as the empirical counterpart of the hazard function, or the force of mortality, as demographers call it. However, we also know that mortality is a stochastic process that can be analyzed with three different functions, which are all complementary. So on one side, we have the hazard function, but we also have the survival function and the probability density function. And these three measures are complementary and interrelated in the sense that if we know only one of these measures, for example, the hazard, we can derive the other two without the need of additional information. And in demography, demographers call the probability density function as the age-at-death distribution. And age-at-death distribution provide a really informative description of changes in mortality over age and over time. So it was a little bit surprising for us that very few approaches had been proposed, or little effort has been done to try to take advantage of the age-at-death distribution to model and forecast mortality. But let's look at this from a graphical perspective, and let's start here to analyze. These are mortality rates in the log scale for Danish females. That is the example that I will work with in this first part of the talk. And here we have Danish females aged 30 to 110 plus. This is the year 1970. And the animation here shows you how the mortality curve over age has been changing between 1970 and 2021. And what you can see is that the mortality curve has been shifting downward, corresponding to mortality reduction or mortality improvement at each age. And we can observe, for example, that, at younger adult ages, mortality has been improving at a faster rate than at older ages. And this, of course, surely provides us with an interesting perspective on mortality developments. But for example, from this graph, it's a little bit difficult to see or to say how the variability of lifespan has changed in the population. That is why we moved from mortality rates to the age-at-death distribution. So this is the same population, same years, same ages. We just switched from mortality rates to the age-at-death distribution. And what the animation shows you is that the distribution has been shifting to the right and at the same time become more compressed. And well, what is this telling us? Basically, shifting to the right corresponds to, if you want, mortality improvement. The mean of the distribution is moving to the right, the mean, the mode. So we have an increasing longevity over time. But also from this, we gain the knowledge that the distribution has become more compressed, or in other words, the variability of the distribution has declined. And this corresponds to lower lifespan inequality. So there is less inequality in terms of length of life within the population. And this is an information that we cannot straightly get from just observing mortality rates. For this reason, myself and Giancarlo Camarda, we tried to develop the model that we call STAD, that stands for Segmented Transformation Age-at-Death Distribution Model, and I will explain why this name soon. So let's start with some notation. We have X denoting age. We have Fx denoting a standard distribution, which we take as fixed, that doesn't change over time. And our goal is to describe, to capture an observed distribution denoted by Gx using a transformation function t that depends on age and on a set of parameters theta. And in particular, what we want is we want to try to express this observed distribution Gx by taking the standard, the f, and transforming the age axis of the standard distribution. So basically what we want is we want to reevaluate the age axis of the original standard distribution on a new age axis, which will give us the observed distribution G. And in particular, we want this transformation function to be a segmented function that depends on three parameters: the parameter S, BL, and BU. Parameter S captures the difference in the modal ages between the two distributions F and G. And the parameters BL and BU capture the change in the variability between the two distributions that occurs before and after the modal age. So BL, L stands for low, so variability before the mode, and BU, U stands for upper, so variability above the mode. So I'm always thinking that presenting a mathematical notation might not be immediate to grasp how the model works. So let's have a look at some graphical example of how this model actually works. So on the right-hand side, we have our standard distribution in black. On the left-hand side, we have this transformation function. And let's start from the scenario in which we want to describe a simple shift of mortality. So just a simple movement of the distribution on the right or on the left. Well, what we define here, our parameter S, that is given by the difference between the two modes of the two distribution, basically allows us to capture this shifting mortality dynamic. So basically what we are doing here is we are reevaluating the standard, the black line, on a new set of age, on a new age axis, basically, that is given by the transformation function on the left-hand side, which is basically a translation of everything. So basically, you can think we are just reevaluating the black line on a different age axis. And as you can imagine, by changing the value of this parameter S, we are able to capture a wide variety of changes of the distribution. However, when we look at the motivation slides, we saw that the distribution was not only moving to the right, but was also changing its shape. And that is why we introduced two additional parameters, the parameters BL and BU, which basically correspond to the slope of this transformation function on the left-hand side. And you can see that BL, for example, has a slope that is greater than 1. So what happens here is that we have that the purple distribution before the mode, because BL captures the variability before the mode, becomes more compressed than the red distribution. So we capture a scenario of reduced variability before the mode, while BU is lower than 1. So you can see that the variability after the mode is actually greater than the one of the red curve. So we have an expansion of the distribution. And again, also here, by changing the values of these two parameters, we are able to capture a wide variety of changes in the variability of the distribution, keeping the mode fixed. Finally, when we combine changes in the three parameters altogether, what we are able to get is a flexible and parsimonious model that, thanks to these 3 parameters, allows us to capture a wide variety of changes of mortality over age and over time. All right, so the question then becomes, how do we estimate this standard distribution? And let's take two, as an illustrative example, let's take 2 distributions, G1 and G2 here. And a naive first approach could be, well, why don't we just compute the mean of these 2 distributions? You see that the mean, that is the black line here, the black distribution, it's sort of a strange shape distribution that is not really representative of any of these 2 underlying prior distribution, G1 and G2. So we think that a better approach to derive the standard distribution is first by employing a landmark registration procedure, which is something that is usually done in functional data analysis, which basically consists of shifting the 2 distributions, well, actually only one here, to obtain so that they share the common mode, a common landmark. And after we shift the distribution G2, we then compute the mean between the 2. And you see that the standard distribution in black is now much more representative of both of them. It has a sort of average variability between distributions, and it's more representative of the 2. We can now move to the more interesting part, the more applied part. So how moving from the theoretical description of the model to the application to observe data. Again, we will focus on females in Denmark here. We have observed death counts and exposures for adult mortality, so starting from age 30 onwards. We start by performing smoothing, as in Eilers and Marx. And this allows us, in particular, to move from the discrete nature of the data to be able to apply this continuous model. And the smoothing also allows us to derive an estimate of the modal ages at death and derive, therefore, the estimate of the parameter S. Next, what we want to do is we want to estimate the compression parameters, BL and BU. And to do this, we simply assume that death counts are Poisson distributed with expected value equal to the product of exposure and force of mortality. And we maximize the Poisson likelihood for each year, and we get these 2 parameters. Once we estimate the parameters, we can then extrapolate them, forecast them, and to do so, we employ the best ARIMA model for each of the 3 time series, and we derive prediction intervals using a residual bootstrap approach. So let's have a look at the results. As I mentioned, we take the observed data, we start by smoothing the data. On the left-hand side, you have the smooth age at death distribution, right-hand side, smooth log mortality, corresponding to each other, basically. We start by aligning the age at death distribution for all the distribution using this landmark registration approach. And we compute the mean of this aligned distribution that provides us with the standard distribution. Once we fix the standard, we go back to the observed data, and we are able to estimate the time series of the 3 parameters. On the left-hand side, we see the shifting parameter S that increases over time, basically corresponding to the shift of the distribution to the right. On the right-hand side, we see the compression parameter. And if we focus first on the BU parameter in blue, we see that the BU parameter is increasing over time, corresponding to a compression of the variability above the mode, while the BL parameter in green is first declining and then increasing over time, corresponding, well, telling us that the variability below the mode was first increasing and then decreasing. Before moving to mortality forecast, we can assess the goodness of fit of the model. We do so here just by looking, for example, at the estimates of life expectancy at age 30 on the left-hand side and lifespan variability at age 30 computed with eDagger. So in gray here, we have the observed data from 1970 to 2021. And before showing the result of our model, we first fit the Lee-Carter model that we introduced before. These are shown in red. And you can see that the Lee-Carter is capturing pretty well the level of life expectancy on the left-hand side. But on the other hand, it is failing a little bit to capture this nonlinear shape of the lifespan variability. You can see that the goodness of fit here is pretty low. And in blue instead, these are the results of our STAD model that you could see are much more are much closer to the observed data. We can move now to the forecast. As I mentioned, we employ ARIMA time series model for the 3 parameters. In gray, we have 1,000 simulations for each of these time series, from which we can compute prediction intervals using the empirical percentiles. And basically, if we combine a set of S, BL, and BU value for a given time point, we can derive the entire curve of mortality. Or if you want, combining the parameters over time allows us to reconstruct the entire mortality surface. So here I show you the forecast for life expectancy and lifespan variability. Again, in red, we have the Lee-Carter ones, and in blue, we have those from our STAD approach. On the left-hand side, you can see that our forecasts of life expectancy at age 30 are more optimistic. They are a bit higher than the Lee-Carter ones. And on the right-hand side, you can see that perhaps the trend, the slope of lifespan variability between the 2 approaches is fairly similar. But importantly, our forecasts, they start much closer to the last observed data point. Another way to look at the mortality forecast is by looking at log mortality forecast rates. And here we have, basically, we are comparing the observed plus the forecast of the STAD on the left-hand side and Lee-Carter on the right-hand side. So these, until this point here, these are the observed rates that are the same in the 2 panels. And then the lines basically correspond to the forecast. And you can see that the STAD on the left-hand side provide a nice diversification of each age-specific rate, while those of the Lee-Carter forecast have a lot of overlap, so a lot of crossing between ages, which is not so desirable. This can be also seen from looking at the same thing, but looking at log mortality over ages. We can see that the STAD forecasts are smooth over age, while the Lee-Carter forecasts are jagged and erratic. And for example, we have that the forecast at age, let's say 105, is lower than at age 98, 97, which is something perhaps not very plausible. Finally, we perform also some out-of-sample validation exercises. That these are reported, these are values taken from the paper. Basically, one way to assess the accuracy of mortality forecast is by comparing, is basically by taking our data, dividing the data in 2 sets. We take the first set of the data to fit the model and to forecast mortality, pretending that we don't know the second part of the observed data. And then we compare our forecast with the observed data that we didn't use in the exercise. So this is a way to basically evaluate the accuracy of forecasting methodologies without needing to wait 10, 20, or 30 years until knowing whether the forecasts are fine or not. And here we have the point forecast accuracy for the STAD model, the Lee-Carter, and some other variants of the Lee-Carter model. This is the mean absolute error for life expectancy, the Gini coefficient, and the log mortality rates. And you could see how the STAD is generally doing pretty well, having lower values of the mean absolute error corresponding to more precision. We have extra information, we have already extended this model to cover. So what I presented here was only for adult mortality. We extended this to the entire age range and also to forecast cohort mortality. And as an outlook, we are planning to analyze and forecast co-specific mortality and to extend this within the coherent mortality forecast strand of research. Okay, I will move now to the second part. We will switch gears now. We will change a little bit the perspective. We will move to age cohort mortality forecast. And also this project is a joint collaboration with Giancarlo Camarda from INED. This is a work in progress, so maybe less advanced than the previous project, but still, I think it was interesting to show some of the current work. So let's start from some motivation here. So after the introduction of the Lee-Carter method, there has been a lot of extensions in more recent years that have been tried, that have been proposed to address some of its limitations. For example, the jump-off bias of the model, the jagged nature of the forecast, as we have seen before, that are very erratic, not smooth, and other limitations. However, we didn't encounter applications of this model to directly forecast cohort mortality. And as you all probably know, if you have studied demography, I think yes, analysis of cohort mortality are very important, and they provide a nice complementary perspective into the standard analysis or more used analysis of period mortality. So for example, when we look at period mortality, we might be interested to know let's say, what was the effect of life expectancy of this recent COVID pandemic for the last 2 years. And this is fine, and this is very interesting, of course, very relevant. However, we should not forget that when we work with period life tables, we are basically working with a model. So we are taking this synthetic cohort of people, and we are generating the life table, assuming basically that this birth cohort will experience these mortality rates for their whole entire life. So we are not allowing for mortality improvements over time. And as we know, mortality improves over time. So this is like a really strong assumption that is not met. So the alternative perspective of analyzing mortality is by looking at cohort life tables. And when we look at cohort life tables, well, we are actually looking at the real mortality experience of a real birth cohort of real person, real people. So we actually take the birth cohort of a given, in a given year, say the cohort of 1900, we follow them through for their entire life, we don't make any assumptions, and this gives us their actual mortality experience. Of course, what is the shortcoming of this analysis is that we need to be patient. We need to have the data. We need to wait until the entire cohort is extinguished in order to be able to construct the life table. So, of course, there is a strong need to try to sort of complete the mortality experience of these partially observed cohorts in order to be able to say something about cohort mortality trends without waiting for these cohorts to die out. And in the literature, there are very few approaches that have been proposed to forecast cohort mortality. Let's have a look at this from a visual perspective. So this is what you are probably very much familiar. That is the age period Lexis diagram. Again, this is Danish females. Here is from age 0 to 100 and plus, from 1900 to 2020. And each cell here corresponds to a mortality rate for a given time and age. So the alternative perspective, the age cohort Lexis diagram here, is basically what this diagram is showing us is basically the same years that I showed you before is just that they are restructuring so that on the x-axis, we don't have anymore the time period, but we have the birth cohort. And we can immediately see how full mortality information is available only for these cohorts, 1900 to 1920. While for the more recent cohorts, the data are missing. Why? Well, because these cohorts still did not die. So we need to wait for them to die out. And the goal of this second part of my talk will be to try to complete this upper right triangle so that we can actually say something about the core mortality for these cohorts. So as I mentioned, there are not many ways to do this. Probably one of the state-of-the-art approaches to forecast core mortality is by using a Lee-Carter diagonal approach. And what we will see in this talk will be also two proposals that are the core Lee-Carter and linear Lee-Carter. But let's start from the state-of-the-art, which basically it's a pretty straightforward, if you want, approach that says, okay, we have the age period Lexis diagram, we forecast mortality in the period fashion, and then we just read cohort information from the diagonals of this Lexis diagram. So visually, again, we have age period Lexis diagram. What we do is we take Lee-Carter model, we forecast mortality until the year 2120. And let's say that we want to know the mortality pattern of the cohorts born in 1950 and in 2000. Well, what we do is we just take the diagonals of this age period mortality surface. As you might think, or maybe not, I don't know, but just by describing this approach, this seems a little bit cumbersome and a little bit inefficient in the sense that if we have an age cohort surface of mortality data, why don't we work on that rather than going into the age period Lexis surface, forecast the age period Lexis surface and take the diagonal? This seems a little bit, at least in my eyes, a little bit cumbersome or not so straightforward, let's say. And in addition, if we analyze the forecasts that are generated by this approach, well, we have a pretty large triangle here in red that is made up of forecasts that we are not really interested about. So in order to do cohort analysis, core mortality analysis for the cohorts 1900 2019, actually what we need is this green triangle. So we are kind of working too much here. So yeah, another reason why I think this approach is a little bit inefficient. And what we could do is we could also have a look at the forecast themselves, actually. So on the left-hand side, we have Danish females. On the right-hand side, we have males in England and Wales. On the bottom panels, we have log mortality over cohorts for age 35 and age 70. While in the bottom panels, we have a log mortality over ages for the cohort 1950, this one, and the cohort 2000. And the blue points here are the forecast of the Lee-Carter diagonal approach. And what we can see from the bottom panels, from the top panels, for example, is that there are pretty large jump-off biases. So the first forecast point, let's say, is pretty far from the last observed point, here, 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 but also here, for example, in the bottom panels. And this is something, again, that is not perhaps so much desirable when we forecast mortality. On a more positive side, perhaps we can notice how the shape of age mortality in the bottom panels follows a sort of nice linear trend, which in a log scale if we exponentiate this, it will correspond to an exponential increase in mortality or a Gompertian increase of mortality, which is something that has been observed in human populations. So this is something, a desirable feature of this forecast. So just to summarize, the Lee-Carter diagonal approach is a little bit inefficient. It has rather large jump-off bias. It has some issues with the prediction intervals of lifespan variability measures, as more thoroughly discussed in Van Raalte and colleagues, but it has a reasonable shape over ages. We can now move to the first first approach that we think can improve cohort mortality forecast. And in particular, this, we call it sort of cohort Lee-Carter method, which basically consists in simply fitting the Lee-Carter model on the original cohort, age cohort mortality surface. So if we simply fit the model, well, then we automatically get the forecast that we are interested in. In order to do this, we have to slightly modify the estimation procedure that is typically employed in Lee-Carter. So we don't use singular value decomposition, but we should work in a Poisson setting in order to deal with the unobserved data that is basically treated as missing data. And an interesting feature of this approach is that the forecast that we are interested in are basically derived from the plain estimation of the model parameters. So we don't need to extrapolate the cohort index as one would do in the period fashion. Let's have a look at this from a graphical perspective again. So we have the age cohort Lexis diagram that we saw at the beginning. We simply fit the Lee-Carter model using the Poisson framework. And what we get is we basically get, without any forecasting, we are able to get the entire age cohort mortality surface. These are the parameters estimated from the model. Top panels are Danish females, bottom panels males in England and Wales. On the left-hand side, we can see the alpha X parameter that is describing the general shape of mortality. Central panels are the beta X, that is the rate of mortality improvement at age X, and the kappa C, that is the mortality, the cohort index of mortality for each cohort. More interestingly, let's have a look at the forecast from the cohort Lee-Carter that are shown here in red. We can see that the problem of the jump-off bias is a little bit reduced. Doesn't disappear completely, but it's mitigated here and here. There are two concerns probably with this approach. First one is that if you look at the top panels, the forecasts are not really linear, but they are much more jagged or sinusoidal. And this this might not be very desirable, especially in the more recent years, because these are basically driven by very few observations. But perhaps more importantly, if we look at the bottom panels, we can see that there is a sort of, especially for the 2000 cohort, there is a sort of sinusoidal shape of the increase in mortality over age. So a sort of departure from the Gompertz model, which is something that's perhaps a little bit disconcerting. So to summarize, the cohort Lee-Carter approach is more efficient, but it still has some problems. It has still jump-off bias, which are a bit smaller. It has some erratic behavior along cohorts. And for recent cohorts, we see this sinusoidal shape over ages. For these reasons, we think that a better approach to forecast cohort mortality is by employing a linear Lee-Carter model that is basically exactly the same as the previous one, on which we put an additional assumption that the cohort index is basically modeled as a linear function. So we put this as an assumption. And then we also adjust the jump-off bias. We still work in a Poisson setting, and again, there is no need of forecasting the cohort index. So these are the older parameters of the cohort Carter approach. And in orange, we superimpose the one of the linear Carter. You could see that the alpha and the beta are pretty similar. The main difference here is the kappa, that is a straight line because it comes from our own assumption. And more importantly, if we move on to the forecast themselves, well, if we look at the top panels, we could see how this jump-off bias is drastically reduced within the linear Carter approach. So we don't have these big jumps here and here. And perhaps more importantly, when we look at the bottom panels, maybe for the 2000 cohort, we could see that the orange triangles that are the linear Carter, they do not show this sinusoidal shape. So they don't show this departure from the exponential, or in this case, linear increase in mortality over age. We can also inspect, for example, the prediction intervals. Here I'm comparing prediction intervals of the Carter diagonal in blue with the prediction intervals of the linear Carter. These are the top panels of before, just with the prediction intervals. We could see how the prediction intervals of the linear Carter, they appear to be a little bit more narrow than those of the Carter diagonal. And what we can do, importantly, is by fitting this model, basically we can reconstruct, we can derive the life expectancy at birth or lifespan inequality for these two populations here. So we have the observed points for life expectancy at birth in the top panels, lifespan inequality in the bottom panels. And what we could see is, for example, that the point forecast for life expectancy between Carter diagonal and linear Carter are pretty similar. The linear Carter prediction intervals are more narrow. While instead in the bottom panel, we could see a little bit more diversification in terms of lifespan inequality measures. All right, just to summarize and reaching the conclusion of my presentation, these are the disadvantages, or, well, summary of the previous two approaches. And we think that the linear Carter is a more efficient approach to forecast cohort mortality, which has smaller jump-off bias and a reasonable shape over ages and cohorts. We performed some out-of-sample validation also for these approaches. These are some preliminary results comparing the cohort Carter with the linear Carter in terms of not only point forecast, but also in terms of prediction intervals. And in general, what we are observing is that the linear Carter is more accurate than the cohort Carter. Perhaps something that we are not very happy about, that we are still working on, is that the prediction intervals of the linear Carter, they widen rather slowly in terms of log mortality rates, and they are a little bit too narrow for life expectancy at birth. So we are trying to improve on this by working on the analytical confidence interval and prediction interval from the Esham matrix. We want to better investigate also back projections that I didn't present here, but if you remember the age cohort mortality surface, when we fit the model, basically we get the upper right triangle, but also the lower left triangle. So we are able to back project mortality and reconstruct the mortality of past populations. That could be also an interesting application. And finally, we would like to, of course, apply the methods to different populations and perhaps study the relationship between cohort life expectancy and lifespan disparity, and extend this in several other ways. These are the references from the presentation. Thanks a lot for everybody for listening. I hope this was interesting for some of you. Would be really happy to talk today or in the future, feel free to reach out to me at any point if you are working on this or interested to have a conversation. Yeah, I would be more than happy. Thanks a lot.
Thank you very much, Hugo. So now we would like to invite Professor Everton to make his comments. So Everton, you have the floor.
Hello, everyone. First of all, thank you for the invitation. It's very nice to comment, especially work of a very talented and young demographer that I know for quite some time. So it's an honor to be here, and I will try to give some. Actually, it's tough to give comments when it's a so nice presentation, so good papers. So to find some spots that you could fill in, it's very tough. It's a tough task, but in general, I will have some actually suggestions for the work. So I have prepared also a small presentation that I will show it to you. Just a second. Okay, here we go. So I hope everyone is seeing my screen. So what I want to present first, actually, what I can say about the two research projects. It's a very stylish and elegant work in general, all of them. It's for younger demographers, I would say it's a good example of formal demography methods application, and also in combination with statistics. So Ugo and Giancarlo, for sure, they are very experts in formal demography, and they know how to do these two things, always combine formal demographic methods and measures with the statistic knowledge. So for that, I would say it's incredible work. Both are in certainly an improvement if you compare with many other forecast mortality models. This is an improvement, especially when we concern the Likert model in its variations. So this is another thing that I would say it's positive about the work. And of course, it brings to light a new discussion about mortality forecast, especially when we are trying to analyze mortality in a cohort perspective. So this is especially the second work, and that it's now an ongoing work with Giancarlo. So what I have from suggestions and comments, there are quite not so many, but I think some of those could be used for a further paper. First thing is, it's too much comparison with Likert and its variants. I would expect, this is actually a suggestion, to compare the stat forecast with other models. I would like to see, for instance, how this model performed in comparison with the model that was presented and now is adopted by the UN, which use hierarchical Bayesian model. So Alkema and colleagues, they have developed this Bayesian model for forecast not only mortality, of course, they also forecast fertility. But I think it would be profitable for the work if you could provide some insights on how to compare with this model, for instance. And the other one, which I think it's very interesting, I think I already had this comment once when I saw Ugo presenting in one PAA a while back, is comparing this stat model, STAT model, with the Beer model. That the date here is wrong, it's 2012, it's not 2021. So Beer has developed a model also for smoothing and forecast mortality. And it was a paper he published in 2012 in Demographic Research. It's the top-house model, and I think it's a very elegant model. He also uses standard, but it's not dependent not so much of the standard. It's a spline model, and I think it could be profitable if I would have some comparisons with the beer, for instance. Of course, he used for probabilities, not for central mortality rates, but I think there's something that just converting probability and rates is possible, so for sure you can compare. And of course, you can also try to compare with more old models like the Hilligan-Pollard, Brass model. So I was expecting more comparisons. It's not with Likert, but also with other ways of forecasting. It's just a question why you use too much the Bayesian inference criteria for choose the model, and sometimes could apply the root mean square error. It's also a way of doing so. Could be done. I don't know if you guys have done it, and what kind of which more of could bring to the table in terms of comparison between forecasting. Another thing that I was thinking is about the smoothing process. To get the parameters M and S, you smooth the data so that you get a continuous information and the mortality surface. And I was thinking about it, how much smoothing could you do that not compromise the estimates? Or in another sense, does the smooth compromise the estimates? If you smooth too much or if you smooth less, how this affects the estimate of the parameters that you use for the standard forecast? And bringing to our context, this is something that I think it would be very interesting, is to see how this model performs with countries that present defective mortality data. I know that most of the work and the models that are developed are using human mortality database, has a huge protocol of quality of information and so on. But I would really happy to see how these models could be implemented, or at least somehow developed and applied in context that you don't have such a good data. And last, concerning this first work, is about are you guys thinking in ways to develop a model that is less dependent of a standard? Reading your paper in the Pop Studies, you use standard Sweden, which we know, and we always say it's a gold standard. But I cite again the work of the Beer. They also use a standard in the top house, but the model, it's more flexible and less dependent of the standard. And as I was reading it, and I guess this standard forecast, sorry, depends much more of the standard that you use. And I don't know if there are ways to avoid that, to get less dependency of the standard. For the second work, which is in progress, the first thing I think could be nice, it's to provide at least a more convincing argument about why it's so important to forecast cohort mortality. I read in the text, I was getting, okay, but most of the arguments that are saying it's about period mortality. So we still stuck in the period. So it's just a more substantive stuff that could be bring and say, okay, cohort mortality is also important because of that. I was not seeing that much in the text. I think it could be nice to provide some more convincing arguments about why cohort it's also important, forecast cohort, in which scenario. So give some examples. So it's more for a broad public, I would say. And this linear Likert model, I also missed a little bit of comparison with other forecast cohort modalities. I give you just a few examples, but I also went to the literature to search for some papers just to get an idea. There are not so many, and you guys are really in the forefront in developing a new thing. So there's this paper presented by these two authors from Czech Republic. They use average ratio cohort-specific rates, which is a very simple way to forecast cohort mortality. It was presented in the EPC 2014. There's also this paper that you mentioned in your work from Rizzi and colleagues. They also forecast mortality and life expectancy cohort from non-extinct cohorts. So probably comparisons with more works and not just stuck with, because at the end, it's a new variant of the Likert that you guys are creating. So probably compare with other methods of forecasting. And this is another curiosity. You presented here, it's not in the working paper, the cohort Likert model, and then that you guys developed, and then the linear Likert model. I was thinking just now, seeing your presentation, if it's not possible to combine both using there's the traditional Likert that you just look at the diagonal and get the information. So you create a synthetic cohort, but why not using cohort Likert model in combination with linear Likert model? I think probably could bring something completely new, or I'm just saying stupid things here. I don't know, but this is something that I got in my mind. So for the rest, I just congratulate again Ugo for the very nice presentation and amazing work. And that's it. I hope I can contribute, my suggestions and comments can contribute to improve a little bit more. And that's it. Thank you so much.
Thanks a lot, Everton. Thanks a lot for the very nice words, kind words as usual, and also for all these very nice points that you raised. Yeah, these are all very valid points. Let me try to address some of those. Let's see. Compare with other models. Yes, that's a very good suggestion that I can see would be a very nice contribution actually for future work. Like there are a lot of new methods that are appearing in the literature, and you are totally right that most of the time researchers, academics compare the model that they propose with the Likert model. Sometimes the Likert and the variance, but sometimes it's only really just comparison with the Likert. And I agree with you that we should move forward, like not only compare with the Likert, because we know that Likert, besides being like the benchmark approach, it also has some limitations. So there are better ways to forecast mortality. Perhaps why this is not done so much, I would guess that it's I'm trying to like defend the forecasting community here. Perhaps like when we try to introduce like the new model, it's already like pretty much kind of quite some work, let's say, to develop the model. So then I think doing like a proper comparison with like, I don't know, maybe 10, 15 models, this would be like a work by itself. So I think this would deserve like a paper by itself beyond proposing like the new model. So but I think it should be done. It's currently missing, so that could be like a very nice project. And all the methods that you mentioned are like very relevant, and yeah, they should be compared at some point. Perhaps like the UN method, I don't know if it's super much comparable, because the current version is still based on the 5 year age groups, but I know that they will release the 1 year age group, so then the forecast might be a bit more comparable in terms of mortality rates, but one could compare life expectancy already, so that would be good. Let's move to the point of defective mortality data that I think it's pretty interesting for this session. Yeah, so I would like to try to test like these methods in context with less perfect data, let's say. And yeah, I think there is ample scope of trying to forecast mortality in other contexts. Usually most of the forecast or like most these application of these new methods are done in new in like the HMD countries because of data availability, or well, data quality. So perhaps like I think this is a very nice and consequential step after proposing like a new model that works well in a good context. Then let's see if this can be used for Brazil, for example. And then when we try to do this, we realize that maybe the data is for 5 year age groups and not the single year age groups like the HMD. So we should adjust the model a little bit, but yeah, it would be possible, of course. It's just yeah, something that I would like to work on. Smoothing. So in the smoothing procedure that we use, we try to be like as much objective as possible. So we use this P-spline smoothing procedure of Eilers and Marx. So basically, the degree of smoothness is basically only dictated by the data. So that should account for differences in population size, for example, and should provide reliable estimates of the model age. Using the RMC instead of the BIC, yes. The table that I showed was the mean absolute error, but which is similar to the root mean square error. So at the end, it's out of sample validation. Okay, so in the first part, I think that was more or less everything. Less dependent on standard. Yeah, well, the STAD model, it's a relational model, so it needs to depend on a standard to be able to estimate the parameter. You can also think about the Lee Carter as a relational model, where the alpha x basically is your standard mortality profile, which is then modulated by bx kappa t interaction. So we didn't test yet how the model performs if we try, say, to make it less dependent on the standard, in the sense that we always estimate the standard from the data. So if we are looking at Sweden, we estimate the standard for Sweden. If we fit the model and forecast in Japan, then we estimate the standard for Japan. So it's like a country-specific standards. But there is a scope also there to try to taking an outside standard, like a regional life table standard, if you wish, and try then to adapt it to the data, or use it in context where there is maybe data limitations also. Again, a possible link with the more defective mortality data context. But it's a really good point. Let me move to the second part of the comments. I agree that we should try to make more convincing arguments for the cohort mortality forecasting. I try to to make them within the presentation. I don't know if people kind of bought the idea. Well, maybe somebody will tell me if that was good or not good. Yeah, but and in the paper we were missing a little bit this part. You're right, it's still a work in progress. So we will try to make it more more suitable, let's say, for demographic, but also non-demographic audience, to try to sell the idea of core mortality forecasting. Comparison with non-Lee Carter approaches. So yeah, there is the paper by Silvia Rizzi and colleagues. The reason why we didn't compare it yet, but we might do it, is that their approach allows them only to complete the cohort experience until the cohort 1960. And we wanted to have something that extended, as you saw, until 2000 and until the cohort born last year. So I think their method works really well. And I also work on a method that is working fine, but it's only for adult mortality. But those are like a little bit more limited in terms of how much you can forecast in the future or more recent cohorts. Thanks for that reference to that paper by Matsuk and Tezarkova that I didn't know. I will check it. What else? There is a question in the chat that I will read. Great work. Thank you, Pablo. Do you have some software, maybe some air packages? I don't have air packages. I didn't develop them yet. It was something to do, but it's still on the list. But all the codes to run the models, the STAD, or other papers that I published, I put all the source codes in GitHub. I can actually leave a comment in the chat with my GitHub page. Not for the cohort Lee Carter, because we are still working on that, but for the others, yes. There is no R package yet. Stay tuned. Probably maybe next year, or well, sometime I would like to do it. But if you're interested, you can even send me an email, and I can provide the code or the links to the. Yeah.
The other question, or the provocation that I said about combining the cohort Lee chart with the linear, is that possible?
Yes. So basically, I don't know if I understood well, but I think they are already combined, in the sense that the linear Lee Carter, it's already a cohort. Sorry, it's a cohort linear Lee Carter. So it's exactly as the cohort one, but in addition, it has this linear assumption. Yeah. So I just put my the link to my GitHub, but I don't know if it appeared in the comments, because I think I put it in. I don't think I can put it in the comments. Well, anyway.
Okay, thank you very much, Hugo and Everton. Such an interesting presentation, awesome data visualization, and high quality debate. I think there's a great space in the demography field for improving the mortality forecasting. And I'm sure this material will be very important for the demography students and researchers in Brazil. So to finish today's sessions, I want to thank the coordination of the Population and Health Work Group, Rafael Guimarães and Giovanni Massimo. Also, thank you, Vinicius from IT. And thank you all who was watching us from YouTube transmission, and see you all in the next ABEP scientific sessions. Thank you.